Assalamu alaikum. My name is Hassan Shahid, and today I am presenting my work on fine-tuning deformable data on document layout analysis. In this project, I took a powerful pre-trained layout analysis model and specialized it to handle custom magazine data, achieving a significant improvement over the baseline. I will walk you through the problem, my methodology, the training pipeline, and the final results. Okay, coming to the problem and motivation, the core problem we are addressing is that standard document analysis model struggle with the complex artistic layouts like found in magazines. Why does this even matter? Because accurate layout analysis is foundational for contact extraction systems, LLM-based applications like QA chatbots. Our solution is that we fine-tune a state-of-the-art deformable editor model on the small, high-quality custom dataset to bridge this domain gap. As an example, I provided a magazine page on the right. It has a complex layout with overlapping elements, varied fonts, and artistic design. Okay, here is shown a deformable editor architecture. It starts with a ResNet 50 backbone, this CNN architecture, CNN backbone. It has 23.5 million parameters, then a flattening layer, and uh, there is a transformer layer with encoder and decoder, which has around 17 million parameters. So a total of 14 million parameters are in the in this model. And then there's a final output layer consisting of two parallel feed-forward networks which output class prediction and bounding box prediction. Because we are doing object detection, there are basically two types of labeling. Uh, a, we are drawing a boundary box and we are classifying what type of object it is. So let me first explain the key innovation in the deformable DETR model. It's its predecessor. It is a predecessor DETR model, which stands for def, detection transformer, and basically it calculates attention for every pixel pair, which leads to quadratic complexity as written O of h square and w square. H is the height, w is width, and c is the number of channels output by the transformer. Uh, so it is pretty expensive. It was pretty expensive to run return models. So the solution uh, provided by deformable editor is that it introduces a sparse sampling, in which instead of looking at every pixel, the model learns to attend only to a small set of key points around reference positions. This reduces computational complexity from quadratic to linear. The it has multi-scale feature aggregation, which naturally handles objects of different sizes, which is crucial for document elements containing small objects and large objects. So it learns to differentiate between them as well. So the model uses a set-based prediction method. First, bipartite matching using Hungarian algorithm. Uh, Unlike YOLO, which uses anchors and non-maximum suppression, deformable data predicts the first fixed set of 300 objects and finds a unique one-to-one matching between predictions and ground truth. This actually eliminates duplicate detections. And secondly, the loss function is a weighted combination of classification and localization losses. Here's an equation written. Loss is equals to this. The lambdas are the weight loss, uh, and these are basically 2, 5, and 2 used by the Aaron model, pre-trained model. This and this is the focal loss for classification. There's this and there's a L1 absolute loss, and there's a generalized intersection over union loss, which ensures bounding boxes are accurate regardless of the object size. So basically, it is invariant, scale invariant precision loss. So here comes our pre-training foundation. I didn't actually start from the random weights. I used a open source model pre-trained on Doglenet available in Hugging Face, and it is actually trained on a uh, Doglenet dataset which has 80,000 pages, which are annotated by human, and that's why it is special. It consists of 6 diverse domains like financial reports, patents, and scientific reports. This gave my model a head start, as it already knew what a generic title or table looked like, but it needed to learn the specific styles of magazines. These are the 11 labels highlighted, which is used in DocLenet labeling, and they are also compatible with our custom dataset. So here's the methodology. Uh, I annotated a custom dataset using Label Studio, mapping the 11 categories of DocLenet, and for training, I chose to fine-tune the entire model, the for all 40 million parameters, but used a very low learning rate. This gentle fine-tuning allows the model to adopt a magazine style without forgetting the general document knowledge it learned from the 80,000 Doglenet pages. So for our custom dataset preparation, I selected 3 magazines and one book, and taking the first 10 pages of each. These pages are often the most complex, featuring tables of contents, editorials, title pages, and dense imagery. This gave my 40 high density pages, which I manually annotated. It's a small dataset but highly targeted. So the raw annotations from Label Studio weren't enough, so I built a custom Python pipeline to ensure data quality. It validates every box, removing any errors. It remaps my Label Studio categories to the exact IDs expected by the pre-trained model. It resizes every image to 1025 by 1025 pixels, which is the native resolution for DocLenet dataset, and for this model architecture. I wrote a fine-tuning script to handle the training. It includes resume capability, which is crucial for long runs, and a live visualizer class. I wrote to track loss curves in real time. This ensured I didn't lose progress even if the GPU crashed or power was lost. the training results was very strong. We saw a 74% improvement in training loss and more importantly, a 50.7% improvement in validation loss. The training loss was initially 0.66 and the validation loss was initially zero point 0.7, so they were very pretty close to each other. And when we trained it, the final uh, was 0.17 in train loss and 0.39 in validation loss. This was the final, not the best. The final, uh, the final had a loss of zero point 0.2 training loss, and sorry, the best model, and the validation loss was around 0.3534, something like that. Which it will come in the next slide. So this was achieved on a single NVIDIA RTX 3060 with 6 GB VRAM in just like around 1.5 to 2 hours, proving that this methodology is accessible and computationally efficient. So one thing I want to add is we use the batch size of 2, which actually used around 6 GB of VRAM. If I increase that, it ran out of memory. So here comes our training dashboard. This was auto-generated from my training script. You can see the steady decline in the training loss and also the validation loss. This top in this top graph. The best model came after 26 epoch. Uh, as I said earlier, it has a validation loss of around 0.35. Okay, the overfitting monitor here at the bottom shows that while the training loss continued to drop, the gap between the training and validation remained stable, indicating that the model wasn't just memorizing the data, it was actually learning. The uh, the loss, sorry, the learning rate was actually varied for, from 0 epoch to 30 epoch, and then it was declined to 50 epoch to avoid overfitting in later periods and see if there's an improvement in the model. So here are the initial losses of training and validation I already mentioned before. So the most critical test for any model is generalization. I evaluated a model on a held out test set it had never seen. The test loss was 0.38, which was nearly identical to the validation loss, which was around 0.389. This confirms the model is robust and will perform reliably on a new magazine pages in the real world. So these are the loss bar charts highlighting the max loss, minimum loss on the test set, and these are the test data distribution. These bar charts, how many text objects were there, how many pictures were there on the test sets. So these are highlighted there. Okay, so coming to comparison with the baseline, here's the headline result: 54.4% improvement. The original on the test set data set. The original model had a loss of 0.834 on this data set. My fine-tuned model brought that down to 0.38. We also saw an increase in average confidence for like 0.486 to 0.504, which meaning that the model is not only more accurate but more certain about its predictions. Okay, now let's look at the visual proof. On the left hand side are the base model results, and on the right side are my fine-tuned results, fine-tuned model results. Notice how it merges when the text columns uh, come into one big box. So it actually fails somehow here, the base model, because there are multiple pictures and there are multiple captions. According to the Doclinet labeling instructions, it should have um, separated out each picture like this, with each caption, each having a different caption. So our model improved on that. It somehow didn't capture this one, but I think these things are more crucial. These things were more crucial. Even the model missed out this section, which consisted of important text, and this picture was also highlighted by our model, added by our model. So coming towards the results on a simple layout, where the base model actually performed good, our model performance remained same. It actually this is important because it shows that my fine tuning didn't break the model's basic capabilities. It retained the knowledge from DocLearnet while gaining new skills from our complex pages. So here is the area for future work. These are the highly artistic title pages. The base model missed almost everything. It only detected two objects: this header, this text, and this picture. Our model also struggled, but added two new elements, and like this text and this this was this it was classified as a picture, but it was still able to bound add a box here. So mm, uh, this suggests that we need even more training data for these specific edge cases. So this is the conclusion, and the this project in conclusion, this project proved that you don't need a Google size data set to get state of the art results. With just 40 pages of high quality annotation and careful fine tuning, we improved performance by 54%. Moving forward, I plan to expand the dataset to cover more title pages and optimize model for real-time inference using ONNX runtime. Thank you. So let's now run our code. The environment is already set up and activated, and we have this dataset prepared for testing inference. This is our test set. These are the train images, and this is the validation set. So let's run batch compare for comparing the baseline model and our fine-tuned model of the test images. This is the command. It runs the batch compare, and it takes two models: the original model, the baseline model, and our best fine-tuned model, which had the best validation loss. And there's the path for test set images. and there a new output directory will be created when it is run. We will run it for a 0.5 threshold. So it is currently running. It's processing the images now. Shouldn't take much more time. So yes, it has run. And let's see the results. The comparison results directory has been created, and here is the comparison of the original model and our fine-tuned model. This is already shown in our presentation. These are like our baseline model already performed well in this type of images, and these our model made a difference, really good difference in this types of images. The this model failed. The baseline model failed to capture this text. And these images were also not. These pictures were also not captured by the base model, and, other things all are captured by the model. This was already presented in our presentation. So we have run the inference on the original model of and our fine-tuned model and compared them side by side.